Okay. Well, good morning to all of you who came probably from far, far away. And some of you, I guess, may be in a different time zone, as I am. I just arrived yesterday, so I'm around 2 a.m. If I say something not quite right, so you're entirely entitled to correct me. And if I fall asleep during my talk, you have to ask me questions, right? So then keep me awake. So the other thing is, when you ask to give a talk, introductory talk at a school like this, a typical problem that we have is just to judge the level of presentation. What exactly, we are not quite sure what exactly you know and you don't know. So maybe it will be a good idea to ask you, how many of you would identify yourself as a theorist? Okay, and experimentalists? Thank you. And how many of you would say that I'm kind of like almost a computer scientist? Okay, good. And how many of you would be familiar with the term completely positive trace preserving map? Oh, well, that's not bad, actually. So maybe this talk is too simple after all. Okay, we'll see how it goes. So that's fine. That gives sort of us a good judgment. That means that we can be a little bit more serious, and my subsequent talks I'll just go a little bit more advanced. But my idea, I'm supposed to give 4 talks here, or 4 lectures, and the first one is going to be very basic, kind of more fun, introductory thing. Even though you're familiar with completely positive trace preserving map, I'm going to start with simple quantum interference and, in fact, a little bit of a history of the field and the context. And then we'll see how it goes, okay? And needless to say, if you have any questions at any point, do not hesitate to ask. Just stop me, and I'm quite happy to change my narrative and go and talk about something else. So now let me just try to master this technology. Maybe this one will work. I think, Max, I will need your help, yeah. Oh yeah, no, it's fine. Okay, so so I think that, as I said, I just managed to. I was calling for your help, but I managed to figure out how to move from one slide to the other. So anyway, so I'm going to say a few. So this is the outline of the first presentation, right? So it's just about a little bit about the context. What exactly is it in quantum theory that makes it interesting for us who want to do information processing with some advantage? And so I'll talk about the history of, the few random thoughts about the history of the field, the history of randomness, the history of, well, the early days where the basic tools that we use, mathematical tools that we use for in quantum physics were introduced. I'll talk a little bit about quantum interference, intro to logic gates, and it's a little bit like the introductory things, which probably you know, but you may just want to hear it yet again. Let me start with the randomness. So one of those features of quantum theory that quite often we are referring to is inherent randomness. And in particular, the randomness in quantum physics is different, right? Because it's not really like a randomness for someone, but if we were to believe the Bell theorem and the foundations of quantum theory, it is inherent randomness. It's kind of, philosophers would call it, it's kind of ontological rather than epistemic. But the whole discussion about randomness goes back to ancient times. And people, as early as 400 BC, were really arguing, when you see something that you cannot predict or sort of like pops up out of nowhere, is it really genuinely random because of some laws of physics, or is it just a question of your perception or your ignorance about this particular phenomenon? And there were two different opposing schools in the early days of Greek philosophy. One represented by Democritus was that all those basic entities which Greek recognized as atoms, thinking about them, of course, in a completely different way that we think about them today. So they actually follow a well-defined trajectory. So if you perceive randomness, it's because you perceive it. It's just the nature itself is not random, but sometimes because of the lack of knowledge, you may perceive something as such. And in contrast, Epicurus, about 300 BC, thought that there is a genuine randomness in nature, that sometimes those atoms swerve from their path, and therefore there is something there, not just only because we have ignorance, but some genuine kind of randomness. And, the whole thing, if you think about this notion of randomness, whether something can happen without any reason, without any cause, was actually quite a big thing in the whole history. And it entered even things like ethic, right? So, for example, if something can happen for a reason, then how to judge your action, for example. Do you really have a free will? Because if there's no genuine randomness, everything is predetermined. If you go into a super deterministic worldview, then how can you possibly be responsible for your action? You do something, right? And you say, well, look, I did this, I committed this crime, but I was predisposed to do this because from the very beginning, even before I was born, probably was already in some larger cosmological model was decided that I'm going to do that. But if, on the other hand, there's a true randomness, you may argue in a different way. There was a neuron there and just, randomly fired, and how can I be possibly responsible for this? So there are different opposing views here, and the notion and the concept of genuine or not genuine randomness has been discussed by philosophers, and I'm only scratching the surface. It's not like philosophers being philosophers, they never reach any conclusion. It's not even about reaching the conclusion. It's about having good time arguing about those things, learning something, maybe being more sophisticated and more precise and more nuanced as you go on describe those things, and it's good fun, right? So the interesting thing is that if you think about it, as we will later on talk about Bell inequalities, about how physicists took the notion of randomness and how cryptologists adopted it and how we use it today for data security, it's amazing that that the whole concept that this has some long and rich history to it. And then it was another interesting thing about randomness is when you try to quantify this, when you try to quantify chance, which is associated with the notion of randomness, right? It took a while actually for chance to be quantified in the proper mathematical terms. There were early sort of approaches to look at the notion of randomness and calculate the means and averages, but the early, so there were like two schools. One was about the theologians sort of discussing about the chance, and so something that I mentioned about the ethical responsibilities and so on and so forth. But the other one, much more pragmatic, that made much more progress in a way, was gambling. So here you have a beautiful picture by Caravaggio about card sharps. So this naive young man is being cheated by those people here who are hiding the cards behind, and the other guy is also looking and signaling with the fingers what the cards are. So there's lots of interesting stuff going on in this picture, by the way, I love it. But the trying to sort of like to figure out whether you have any rational way of winning in the game of chance was actually the first thing that people started thinking seriously, started trying to quantify the whole notion of chance. And what I like in particular here is this character. When I give lectures in Oxford on quantum physics, I usually start with this person called Girolamo Cardano, because when you think about it, we have two basic tools that we use when we do quantum physics today. So mathematically speaking, there are two things. One is probability. The other one is the sort of complex numbers. And so we use probability amplitudes to calculate probabilities. It turns out that the two tools that we use today go back to the same person, to this chap here. And he was a very, very interesting character. So he lived in what is today mostly Milan and Bologna, in the late of his life in Rome, in the 16th century. And he wrote just about everything. And he was known for his work in mathematics. He was a famous astrologer. He was also a good medic and a lawyer. And at the time, in the 16th century, you could afford to be good at so many things. He also wrote a very, very interesting biography. He described himself as hot-tempered, single-minded, given to women, cunning, crafty, sarcastic, diligent, impertinent, sad, treacherous, yada, yada, yada. So I think external sources confirm that it's probably honest account of his. So as I said, he came up with the two tools that we use today: complex numbers and probability. So probability, the whole stuff, if you think that the probability theory was actually cooked up by the bunch of French mathematicians, you're wrong. Actually, he came about 1 century before. The thing is that as a gambler, he had some kind of notes and a set of manuals, and they were not published until his, it was posthumous publication. So he passed away, and then those things were collected by some of his colleagues and students and put together. So the book, or the essay on probability, Liber del Ludole, was published after his death. But nonetheless, he was the first one who tried to quantify probability, to quantify randomness, to quantify chance. And mostly for the purpose of fair game. So he wanted to understand when the game is fair, when you play against someone. And at the same time, he's well known, of course. If you know Cardano, you may know him primarily because of his work in mathematics and solving cubic and quadratic equations, right? And so this was a huge book, Ars Magna, that he published in the 16th century. That's one of the most influential books in mathematics in Western history. So in that book, he introduced complex numbers for the first time. And this, I'm using modern terminology, complex numbers, right? But at the time, it was not really presented this way. So, and here, in the 16th century, believe or not, even negative numbers at the time were a little bit suspicious, because people thought about numbers as representing something solid, like a length or area or volume. And so negative numbers were kind of okay, but to take the square root of a negative number was a little bit weird, because mathematicians thought it didn't make sense. And And so this, the reason he started playing with what we call today complex numbers is because in this book, he is considering a problem. Find two numbers which sum to 10 and the product is 40. And so then he works it through, and in the modern notation, you can see that it involves square root of minus 15 at some point. And but they didn't have the modern notation. So look, this is the part where he writes 5 plus the square root of minus 15. So it's, this is 5 plus, so that is redux. So that's the square root, the symbol for square root at the time, minus 15. And so that's the, that's how they were doing the calculations. And as you can see, to some extent, if you improve notation, if you have more compact, more concise notation, it's much easier to do calculations and you can make progress. So with this kind of notation, it's amazing that he managed to come up and look at the problems like this. But he didn't, even though he sort of wrote down square root of minus 15, and the square root of minus 15 was the first complex numbers we know that was written down in the history of mathematics. It was not square root of minus 1, just square root of minus 15. But he didn't like them. He thought that those numbers were absolutely useless, and therefore he didn't pay too much attention to them. And so let's leave Cardano for a moment on the complex numbers. We'll come back to complex numbers in a little bit and go back to probability. So probability, even though Cardano was the first one to write about probability, so he wrote, he tried to quantify it, just to measure probability or chance of something happening. And he kind of came up with the idea that probability is sort of a number of cases in favor of something happening to the total number of cases that are relevant for this particular problem. And that notion, of course, was formalized later on, but somehow, interestingly enough, mathematicians were not very keen to embrace this. So probability was a little bit fuzzy topic. And even if you take this particular definition of probability that probably many of you came across when you were at school, that if I want to calculate probability, I consider a set of all possible events, right? And then I take the events that are relevant to what probability of I want to measure, so corresponding to, say, if this probability of some event A, so you take number of cases in which A occurs and divide the total number of cases. And there is a problem, though, with this definition. This only works if you assume that all those cases are equally likely, right? And so here we are. We have a circular definition. We want to define likelihood, and we use equally likely in this definition, so which is not quite right. And there were some other issues with this, and not only on the mathematical side, but also about how shall we understand probability. Is it in terms of, again, the whole, old discussion popped up. Is it subjective? So there was an Italian mathematician and statistician, Bruno De Finetti, who said, well, it's very subjective. It's just a personal belief. It measures how much are you prepared to bet. So kind of a Cardano school, in terms of betting things. But, the Austrian guy, like, for example, von Mises, would say, well, it's about frequencies, about something. It's reflected in frequencies. And if, some other people like Karl Popper just said, oh, well, it's objective. Every object has a propensity to do something, and so on. The end to the story, at least from the mathematical point of view, came with a Russian mathematician called Kolmogorov. So Kolmogorov was like, he found a very mathematical solution to the problem. You say, I don't give a damn about whether this is subjective, objective. What I'm going to do, I'm going to define it. So he specified 3 axioms. Say that probability is a non-negative number, somewhere between 0 and 1, okay? Probability that something happens is equal to 1, and then, and that's the interesting one, if something can happen in mutually exclusive ways, we add up probabilities. And he said, end of the story, you know, anything that conforms to the 3 axiom, I call probability, and don't ask me whether it's objective, subjective, or whatever. And he wrote this in a very, so that mathematical terms, he introduced a concept of measure, and probability was an example of that, right? In this essay, actually a book, in a very impressive German title, you know, you like those big words, right? About the foundations of probability theory. So for mathematicians, that was okay. Essentially, from this moment, mathematics took off, and people started looking at the probability and work on it and develop this as a mathematical topic. It didn't, of course, resolve the question whether it's subjective. So the thing is, you know, at the level of axioms, so the Kolmogorov said, okay, I give you a set of rules how to play with that. Where those numbers really come from, how do you get them in the first place? The numbers that conform to the 3 axiom is your problem. Once that could be from nature, that they can represent some properties of something, but that is not relevant for a mathematician. You simply just have them, and I tell you what is a proper, consistent way of playing with them. So if you have probability of those basic events, how you can calculate probabilities of more complicated things. So that was essentially Kolmogorov. And it's all very well, you know, but if you look at the 3rd axiom, which is very important here, that if something can happen in 2 mutually exclusive ways, then you should add probabilities corresponding to those individual contributing events separately. So that's Kolmogorov additivity axiom. But you know, Kolmogorov, and being a mathematician, and nature doesn't care about mathematical structures, right? So nature doesn't follow it. Why should it be following in the first place? So Kolmogorov postulated this. Of course, it was based on some kind of a rational feeling or rational, whatever his motivation was. Of course, I don't know, we don't know, but certainly it was based on his experience, on experience that we have observing the nature. But as a matter of fact, there's no a priori reason why a physical theory or physical nature itself should follow any postulated mathematical theorem, right? There's no reason whatsoever. And nature doesn't even follow. Nature doesn't know about Kolmogorov axioms. So nature simply ignores, as we discovered, the 3rd axiom. So when the 3rd axiom, if you take something that probably you learn in your elementary intro to quantum physics, if you take a double slit experiment and you have a source of particles, usually photons, and then you have 2 slits, and then you have a point on the screen somewhere, and a single particle can take one of the 2 paths, right? Can go from the source to the final destination there. And if the probability of taking one path is P1, and probability of taking the other is P2, the probability that it will end up there is P1 plus P2. But then if you set up an experiment, that's not exactly what happens. We have counterexample to this claim. So nature doesn't really follow this. And that means that in order to describe behavior of elementary particles, we have to modify probability theory. at least, you know, we have to do something about the Kolmogorov third axiom because it doesn't quite work this way. And of course, we know how we resolve it today. We simply go one level below probability. So we go to more fundamental level and say, actually, maybe probabilities are not fundamental thing. Maybe there are other things, in this case, complex numbers, so-called probability amplitudes, so that we add probability amplitudes, not probabilities. And when you add probability amplitudes, we always get probabilities from probability amplitudes by taking mod square. So I have, whenever I have probability amplitude, I take mod square, bingo, I have probability. But that has consequences. So if you just add probability amplitudes in this diagram here, then you do, and if there's, from this lecture, as I said, if there's just one thing to remember, is probably this slide, is that it's like intro to quantum physics, right? So if I can somehow attribute probability amplitudes to individual trajectories, individual events or processes. So in this case, I attribute probability amplitude alpha 1 for the particle to take the upper path, probability amplitude alpha 2 to take the lower path. And then let me write alpha 1 and alpha 2 in terms of the modulus and phase factors. So I have a phase factor, phases phi 1 and phi 2 associated with those two paths. Okay, and then following the rule, we take the sum of the probability amplitudes and take mod square of that. And if you take mod square, you will get mod square of alpha 1, mod square of alpha 2, but that's not the end of the story. And here exactly where things become interesting, here exactly where quantum physics becomes relevant. So we have one extra term here, which is a cross term. So if you write this, if you take into account that alpha 1 mod square is equal to P1, that's the probability that the particle will take the upper path, and then we have a probability that the particle will take the lower path. So until now, it's Kolmogorov, right? Until now is the third axiom of Kolmogorov. Until now, it's just a classical probability theory. But it's corrected here. And it's corrected by this one extra term. And what is interesting in this term, there are two things that are interesting about this interference term, as we call it. First one is that it could be positive or negative, right? So as compared to classical probability theory, this quantum addition here allows you to decrease probability or increase, right? So we have constructive interference where you can amplify the probability. It's more than a classical probability theory would predict, but you can also make it smaller if it is negative. So you have destructive interference. So that's the one thing. So that means that as compared to classical physics, quantum physics allows you to enhance things or suppress things. What does it depend on? So you can look now at those phases here. And that's something very interesting there, because you can see that there's a phase difference between phi 1 and phi 2. So the probability, the particle, is just a single particle, right? Going from the source to the final destination reacts to the difference in phase settings. So how does it know about the difference? You know, it doesn't react to this number on its own, doesn't react to phi 1, doesn't react to phi 2, but reacts to phi 1 minus phi 2. So that's a little bit weird when you think about it. So how come a particle knows about those two trajectories at the same time? Because it does have to know about them in some way in order to be able to react to the difference between them. And that's one of those first mysteries of quantum physics. And at this point, people just take two different, or maybe a few more different approaches. Some of them, you know, shrug your shoulders and say, well, it is what it is, right? And the others say, well, it obviously must somehow travel through, take two paths at the same time. but it's a single particle, and we never see any fraction of a particle. So that's a bit mysterious. And some people even try to rescue Kolmogorov axiom, saying, aha, look, Kolmogorov says quite clearly those have to be two mutually exclusive events. But now, maybe those events are not exclusive. Maybe the particle is a little bit, going this way and this way, so they're not quite exclusive. That's why it doesn't work. You don't listen to Kolmogorov here. Maybe, right? So I leave it to you. I'm sure, you probably haven't thought about it because it's just bread and butter of modern physics, right? So you just write those interference terms. But when you think about it, it is actually a lot of, if you start talking about this, there's a lot of interesting stuff there to think about. And then if you want to point at the difference between quantum and classical, that's this term, all physical review Nature papers written about quantum physics are essentially a kind of less or more sophisticated discussion about the interference term. Without the interference term, there's no quantum. That's exactly where quantum comes from. And how does it enter our field, quantum information science? Well, okay, but well, before I just come into this, I just say that, of course, physicists learn how to play with quantum interference. And you may say, how we implement quantum interference? How do we see this deviation? So we see it in all kinds of ways. We can see it with photons building quantum interferometers like Mach-Zehnder interferometer. You can do it with ions. You can do it with cavity QED, where you throw atoms into cavities. You have essentially three components, three cavities. You have an atom. Atom goes into a resonant cavity, interacts, so that goes from the ground state somewhere between ground and excited, goes to the off-resonant center cavity, where it gets a phase shift, and then goes into another off-resonant cavity and finally gets detected. You can do interference with neutrons, with trap ions. You can. Wherever there is a quantum technology, there is a way to do interference. Otherwise, it's not a quantum technology, essentially. And so the most classic one, probably many of you see, is Mach-Zehnder interferometer that allows me maybe just, and there are many isomorphic systems to this, using a mathematical term, right? So let's look at this quantum interference again in order to introduce a concept that we are going to use later on. So in a Mach-Zehnder interferometer, classic interferometer, you have a single photon. I know that single photon is sort of like a strong statement, but for theorists, it's just a single photon impinging on a beam splitter. And the first important component of this quantum interference here is this first beam splitter. The first beam splitter has a role. It just prepares quantum interference. It opens quantum interference. It just generates two possible paths for the photon. In order to have quantum interference, we need at least two paths, right? So, and the first beam splitter here says the photon can be transmitted, can be also reflected. And then you let the photon go into the schizophrenic state, right? Being reflected and transmitted. And then you put pieces of glass in between the phase shifters. So it gets a phase shift. So here the sort of will be measured by optical path, right? So it will slow down a little bit here and there, depending on the thickness of this plate. And we'll acquire phase shift on this path. So we have the second very important component of quantum interference. We have to have a mechanism to introduce phase shifts. And then that's not good enough, because if you were to put photodetectors on each of the paths at this point, you would detect a photon either here or there, and nothing interesting would happen there. In order to see interference, you have to close the path, right? You have to bring them back, and the second beam splitter does the job. So it just brings together the path, and you put photodetectors, photodetector 1 or photodetector 2, and then it will start clicking. And if you repeat the experiments or measure probabilities of clicking, you will notice that the probability whether the photon will end up in the detector 1 or 2 depends on the difference in the phase setting of two optical paths. So on the difference between phi 2 and phi 1. A more generic description here is this diagram here, which shows those two sort of different paths, also the different states of the photon, where the photon is placed, are represented by those two horizontal lines here. And the photon starts in this path here. And at this point, we have the first operation, the beam splitter, or later on we'll be talking about the Hadamard gate, which plays the same role. So the photon here, with probability amplitude 1 over square root of 2, is transmitted. But with probability I over square root of 2 is just reflected and goes into a different state. Then the phase shifters, they introduce phase factors e to I phi 1, e to I phi 2. And the second beam splitter here, again, allows you to close the interference. So the path the photon goes this way. There is a sort of a bifurcation here, follows through those two paths. And then the probability that it will be detected here is just, you have to combine the two paths and you see the interference at the detector 1. You can also see the effect of interference at the detector 2. So we have three components, again, beam splitter, phase shift, beam splitter. In general, it's translated into the golden sequence, which we recognize, which is behind every single quantum algorithm that you will ever discuss seriously, is the sequence Hadamard, which represents beam splitter. Slightly different phases there, but essentially, instead of I factors, this is the Hadamard gate. And we, instead of sort of like trying to understand this in terms of the dual rail, we say, okay, we have a particle, we have a single photon, we have an ion, we have an atom in cavity QED that goes through the first cavity, Hadamard operation. The second cavity of resonant, phase shift. Again, the resonant cavity. So we have a sequence, whatever Hadamard represents, it can represent a beam splitter, it can represent a resonant cavity, it can represent a pulse of light, which is sort of shine on an ion trap with a resonant frequency. We don't have to know all those technologies. It will be very difficult to do this field, adjusting or sort of customizing our description to technology. We have a very generic description. We say we have a Hadamard gate, and you experimentalists, you implement it using your tools. And then we have the phase shift gate, and you experimentalists implement it using your tools, your preferred toys, right? And then we have Hadamard. So any single qubit, and then we have, of course, a two-level system that we call a quantum qubit. Every single two-qubit quantum interference can be represented as Hadamard phase, Hadamard sequence. So it's Hadamard phase, Hadamard. And you will see it over and over again if you study quantum algorithms. And then at the output, we have interference that shows quite clearly, because if you want to measure whether a qubit is in state 0 or state 1, the difference in the phase setting becomes very important. And then, the whole thing is behind many things, not only behind quantum algorithms, but all kind of measurement techniques were developed for high precision metrology and all kind of stuff that we will not be talking about this. So this, of course, and then of course there's much more to it, because we do need more than one qubit, of course. So we have not just a single qubit interference in computing devices, but we have a multi multi-qubit, many qubits involved in more complex quantum interference where quantum entanglement comes into the game, but we'll come to this later. What I like about the whole thing is that even at this level, we have also something very interesting, something very challenging for people doing conventional logic. That's why this field was such a great fun in the early days. You know, in the early days, it was a bunch of mathematicians, bunch of computer scientists, bunch of philosophers, logicians, physicists, who kind of every now and then talk about those things. And it was interesting to see with what kind of prejudice you come to the table when you are working in your own field. So for example, so here is like the one I liked a lot, which I discussed a lot with Bob Solovey, one of the logicians. So if I ask you a following question, look, talking about logical operations, is it possible to have a logical operation, something that operates on a single bit, and that something represent that something as a black box? Apply it twice, and you get a logical knot. So therefore, you know, call this black box the square root of knot. Is such an operation possible? So if you talk to a logician, a mathematician, say, of course not. You know, how come? You know, square root of knot, it's just, there's no operation that has this property that when you apply it in sequence twice, and those are independent application of the same operation, that they will flip the bit value. So you can prove it, right? You see, okay, there are only 4 Boolean functions operating on a single bit. What do we have? We can have, how do we map a bit to bit? It could be constant at 0, constant at 1. It could be identity, so whatever comes in, the same thing comes out, and it could be negation. Whatever comes in is negated, it comes out, right? It's only 4. And neither of the 4 satisfy this property that if you apply it twice, you get something negated. So therefore, a logician goes QED. You know, that's proven that there is no such an operation. And then you go to someone's lab, and that person can show you, can build a device that will implement this operation. So here's one box independently, here's another identical box. They operate independently from each other. I prepare, you know, pick up your physical realization of a qubit, say 2-level atom. It goes through, and you know, it's flipped at the end. And we do know it does exist. And of course, quantum theory explains how it exists. It's another example like a beam splitter. It just allows you to go with certain probability amplitudes from one place to the other, and it's a quantum interference working essentially for you in this particular case. And then, facing with this dilemma, would a logician be prepared to introduce this logical operation, the square root of knot, to the repertoire of logical operation? And then physicists say, of course you should, you have to. Why? Because the physical representation of this operation does exist in nature. So you are living in a state of denial if you are not recognizing that it does exist. So your logic is just, you know, maybe interesting but useless. And you'll be surprised. And of course, you know, logicians are not that stubborn. So sooner or later, they will recognize that there is a problem there. They have to do something about it. But it took them a while to recognize the fact that nature of physics, not just abstract construction, have something to take, you know, to teach you about the logical structures. And probably today, if you go to a conference and talk to logicians, then you'll see it'll be probably 50-50. Some of them would be willing and some of them would be less willing to accept the fact the square root of knot is a valid logical operation. And those working in quantum computation have this logic gate. And then you can also have a similar gate, the square root of swap, which operates on 2 bits and just simply swap the 2 bits. And it turns out that those two, the so-called impossible operations, when you combine it with another impossible operation like the phase, are enough to just pretty much perform any computation of your choice. So here I just, well, that was my way to come up. And so David Deutsch, who was the pioneer of quantum computation, as it happened, he was also my supervisor, so I had a number of interesting conversations with him on this and about the connections between the physics and mathematics. And so yeah, if you want to construct like in conventional computation, you need essentially two logic gates, right? If you have even one, NAND will do the job. So to construct any logical operation. So in quantum computing, you have a freedom of choice. There are many interesting choices of universal gates, but you might as well choose those classically non-existent operations to do quantum computation. And one way to explain quantum computation to people is to say that, you know, every single time we discover new physics. So first of all, you know, computation is a physical process. You know, whatever is your take, whatever mathematical model you choose for computation, if it is not a physical process, it might be interesting from a mathematical point of view, but probably not so interesting for someone who wants to run computation. So it has to be a physical process to be of value to you. So clearly, computers are physical objects, it's a physical process, and what we can do, what we can compute, and how we can compute depends very much on the physics behind this computation. Every single time you discover new physics, you can construct new logic gates, like square root of naught, for example. And that allows you to do computations in a way that people couldn't do before. So there's a natural progress. And quantum computing is essentially about using new set of instructions, such as the square root of naught. The square root of naught doesn't make sense to a classical computer. You cannot instruct classical computer, say, look, I designed this algorithm, and now I ask you to take the square root of naught. The classical computer wouldn't know how to do that, but a quantum computer could. So therefore, you, in your programming language, you have new instructions which you can use for the purpose of computation. So that's one way of telling a journalist what quantum computation is, why is it so more powerful. I don't know how much more time I have.
It's up to you, the slot is 2 hours. You can take a small break and come back, and we'll say 1 hour and a half.
Or maybe if you can survive another 20 minutes, can you? So I'll just go on for another 20, okay? But if you violently object to this idea, well, actually, you know, yeah, you're free to walk out anytime if you don't like it. So this is actually the way we build quantum circuits. And of course, the set of basic quantum logic gates we use for quantum computation today may differ. It's just quite often we use just a phase gate, control not gate. Those who are into the field, the most important thing is that we go beyond the set of the so-called Clifford gates, but we can talk about it some other time. So, and then you can approximate any unitary operation, any quantum computation with arbitrary precision. So if you think about going back to quantum interference, about the mental model that many of us have, well, at least, you know, I have, I don't know what kind of mental model of computation you have, of quantum computation, but one way that I try to explain quantum computation is this. So think about computing device as a device that has a well-defined configurations. So those dots, the vertical line of dots just represents configuration of my device. And time is a horizontal axis here. So if you take a conventional classical computer, a deterministic one, it starts in a certain configuration that you call input, right? And then you make the first computational step, and the algorithm directs you into another configuration. So then you go yet into another configuration, yet into another configuration, and you follow a sequence of computational steps that, if your algorithm has any sort of sense, will take you into the final configuration. Will stop and say, this is your output. You look at this configuration and it represents something, it represents a solution to your problem. Okay, so that's a conventional, classical, deterministic computer. You can, of course, run computation also allowing chance. So there will be a classical Kolmogorov way of doing this. You can say, oh, in the process of computing, my computer can take random decisions. So I can go from input to, with certain probability, to this configuration, but with some other probability to that configuration. And then you just take, you can consider taking one of several computational paths, and you end up in the final configuration. And the probability that you will end up there is the sum of the probabilities corresponding to individual paths, right? Now, we know that there are many randomized algorithms that we use today. They're useful. Whether they are inherently much more powerful than classical deterministic is not entirely clear. There is, in computer science, there is a whole program called de-randomization. We know that today we have some examples of algorithms, the randomized algorithms, that do better in terms of efficiency than deterministic algorithms, but we don't know whether they can be de-randomized. So there are examples, for example, in the canonical example of randomized algorithm that is doing better than the deterministic one was testing whether a given number is prime or not. So randomized algorithms could actually do that with a very good probability of assuring you that this number is prime, for example. And we didn't know any efficient classical algorithm, but it was found a few years back. So now there is a conjecture that most of those randomized algorithms are not necessarily more efficient. They sooner or later will find deterministic. So this is still an open question, and I'm not going to discuss this. But you can see that we can see here that a natural progression. At least, this randomized computation will not be less powerful than deterministic. But we can see the progression from deterministic, using choice, using randomness to our advantage in the process of computation. And the next step along those lines is going to quantum domain. In the quantum domain, we do exactly the same as we do in probabilistic or randomized computation, except that we don't go from one configuration to another with certain probability. We go from one configuration to another with certain probability amplitude. And that has an advantage, of course, that now our computing device goes into the final configuration, and there, the probability that it will reach this final stage is the sum of the probabilities that you take individual paths modified by this interference term right here. So as compared to randomized computation, quantum computation gives you this extra interference terms that we are familiar with. And now we know that this extra term could be either positive or negative. So what does it mean? That if you construct your quantum algorithm well, you can amplify the probabilities of good answer and suppress probabilities of wrong answers by playing with those phase factors here. So you have one extra degree of freedom here that you don't have in any classical way. Your computer will end up in a final state, and if you are clever and you know how to design those algorithms, then you can amplify the probability of the correct output by constructive interference, and you can suppress the probabilities of wrong answers by destructive interference. So that's a sort of a high level of looking at quantum computation. And of course, you know, the reason why we are doing this is because we believe that designing new algorithms, we can design algorithms for the same problems that we already know, but there are algorithms which are more efficient. Now the question is, what does it mean to have an algorithm what is more efficient? In fact, when people say that quantum computers will be faster than classical computers, this sentence is questionable. Most likely they will be slower than classical computers, because if you are involved, if you're an experimentalist, if you are involved in any attempt to build a quantum logic gate or whatever, anything that computes in quantum way, you know how difficult it is, how many components it involves. You know, you have a cooling system, you have optical, you have the whole stuff. And any sort of even a simple computational step in a quantum computer will be much slower, will take much longer, will be a much complex process. But that's not the point. Whether it's really faster or slower doesn't matter here that much in terms of really clock time. What really matters is that you have a new set of instructions, so you can construct inherently new algorithms that do not have classical counterpart. And in this case, efficiency is measured in scaling. So what does it mean? So this is a one slide introduction to computational complexity, right? So you effectively, if you take any algorithm and ask yourself, how good is this algorithm? So what you do, you take a problem that this algorithm is solving, and you run this algorithm, but you increase the size of the problem. So for example, if you have algorithm for multiplication, so you multiply two one-digit numbers and measure how long does it take. Then multiply with the same algorithm to two-digit numbers, to three-digit numbers, to four-digit numbers. So you increase the size of the input, more and more bits at the input, and apply the same procedure and look at the execution time, how long it's going to take for your algorithm to deliver the answer. And then you look at the scaling. So sometimes, you know, obviously it will take longer if you increase the input size because the number of operations will be more, but how much more? So if the scaling with the input size, L, is at most polynomial, so if it is logarithmic, it's linear, it's polynomial, then computer scientists are happy. They say, oh, well, you know, this is good. This scale's fine. If it is quadratic, I can live with that. It's not as good as logarithmic, but it's okay. However, if it is exponential, then nobody's happy about it because it grows too fast. So that means that you will run out of time or any other resources, perhaps. There are some other ways of, I'm not going to go into all nitty-gritty details of, we can also look at the use of memory and so on and so forth. But essentially, anything exponential is bad. And it was, I found, my experience teaching in Oxford was that it's much easier to explain this, that it's bad after pandemic, after COVID than before COVID, right? So any exponential growth is bad, and it's really fast. So in this case, computer scientists divided problems into complexity classes. So the set of problems that can be solved on a conventional deterministic classical computer in polynomial time, so that it scales only as a polynomial, that set of problems is in class P. Everything else that is not in P may take exponential time, right? So it's outside P. But there is an interesting class of problems in between that is called NP. And for some historical reason, NP stands for non-deterministic polynomial, never mind. But it is a class of problems where it's extremely difficult to solve it. So it's exponentially difficult to solve those problems. But once you have the answer, at least you can verify that the solution is the correct one. So we have two things here: solve the problem, but you know, sometimes you can solve the problem and you've been working very, very hard to solve the problem. You have the answer, And to verify that this answer is correct, it requires also working equally hard. But there are problems like, for example, factoring. On a conventional classical computer, you have to work exponentially hard to get the answer. So if I give you a huge number, you work hard and then you give me the answer. But then the thing is that to verify that the answer is correct doesn't require working that hard. You can do it in polynomial time, just multiply those two numbers and you have the answer. So there is asymmetry here. Not everything that is difficult both ways. Sometimes it's difficult to find the solution, but to verify that the solution is okay is easy. So, so then, of course, you've probably heard that the big thing, if you want to be famous among mathematicians, then you should just drop everything and work on this problem where the NP is equal P. So it's just a question, it's outstanding conjecture that maybe this or maybe it isn't, whether all problems that can be verified in polynomial time actually belong to class P. There is also a I mean, this is a gross simplification. The whole field of computational complexity, as fascinating as it is also relatively, as compared to physics, for example, or mathematics, and most of the mature areas of mathematics, is relatively new. And the reason we don't understand the difficulty is when you look at the proliferation of different complexity classes. If you look at the proper diagram, taking into account all computational complexity classes that computer scientists consider these days, it's like a zoo of those complexity classes, and relations and connections between them are equally complicated. So this picture is grossly oversimplified, but and even this is very simplified. So this actually means that when you once you understand what it means to have whether your algorithm is efficient or not, the next step is just to say with respect to what kind of computation. And honestly, computer scientists got only excited about quantum computation when they learn that it has impact on computational complexity. It's just because quantum computation is inherently different. So you can introduce new complexity classes. Problem that is difficult and may remain difficult for classical computers may not be difficult for quantum computers. And the two relevant classes here that we talk is this BPP and BQP. Yes, please.
Yeah, someone recently published a paper that BQP is not really in NP.
Sorry?
Someone actually published a paper that proves that BQP is not in NP.
Whether BQP is not in NP. Well, because, this in some sense, yes, because, this diagram is not entirely correct. So you're right. So it should just stretch a little bit outside this. So it's not, inclusion is not strict here. But what I'm saying is that essentially what is important here, BPP is a class of problems, a class of randomized classical algorithms. BQP is a class of essentially quantum algorithms. B stands for, bounded probability, so that you get the answer. The answer you get, the computer may deliver only the answer with a certain probability. You may want to run this computation several times. But the thing is, the zoo of computational complexity is so huge that only shows where we do not fully understand this field. Hopefully, with the progress of our understanding of the difficulty of problems, we will be able to reduce the number of complexity classes. And of course, the whole point is just of quantum computation today is to find as many problems as possible that are believed to be in BQP, but not in BP. So just like factoring, for example. that we have a problem that we know how to solve on a quantum computer, and we don't know quite how to solve it on a classical computer. What is even more embarrassing is we cannot be sure whether it cannot be solved on a classical computer. Maybe it can, maybe, but we simply don't know. We know how to find a quantum algorithm for this. Now, there is probably much more to, I mean, the focus, of course, of today is to find algorithms where you can see the advantage of quantum computation, but one should not just forget about sort of, when I was talking about the square root of naught, about some kind of inherently different nature of quantum operations. And I think it may have a profound impact on not only on complexity classes, but also on, say, mathematical logic. So for the sake of the argument, imagine the following situation. Imagine that you have a logical proposition, something that you want to prove whether it's true or not. And you know that perhaps you can actually prove it, but proving it would require enormous computation, checking various things and so on and so forth, you know, like map coloring problem or something. And in order to do that, you set up a quantum computer. And quantum computer goes into those different superpositions and comes with the answer and say, yes, this logical proposition is true. The problem is that you know how it works. You cannot stop this quantum interference because you would destroy it if you were to just measure something. So would you believe this kind of proof that this logical proposition is true? Usually when you think about conventional proof, it's like a mathematician to a mathematician. You go and say, okay, a mathematician comes into the room and says, I prove this conjecture. And then you say, show me. And what does it mean? So the guy will just say, okay, let's go to the blackboard, or let me just show it to you on a piece of paper. And you go and step by step, you check whether whatever he or she did is correct in terms of the rules of inference. So you are asking for a physical record for your inspection, right? You are asking, show me the physical record of your computation so that I can go step by step and verify it myself. In this particular case, there's no chance to get the physical record, because if you have something like, say, if you operate on 100, say, quantum bits or more, then the number of those things in superposition is such that to produce a physical record, you wouldn't even be able to do it. There would be not enough atoms in the entire universe. So in this case, how would you believe this proof? You understand quantum physics, you understand how this device is working, but you cannot stop this device and check the state because it's not going to work. So you have to assume, you have to buy, so to speak, that the whole quantum process that took you from the input to the output is doing exactly what you believe according to the best physical theory it's doing. So would you be willing to change the notion of physical proof from a physical record to a physical process? So here, instead of a physical record, I give you a physical process. And this physical process, you understand, you know what the thing is doing. Will you accept this as a physical proof or not? As a valid mathematical proof or not? Again, you know, if you talk to logicians, they are divided on this very much. So some of them say, yes, well, reluctantly, I would have to go outside the logical structure, trust physics, and then believe this. In fact, you know, even when you when you go through a physical record, then you also indirectly have to trust physics in order to do that. But you know, just to show that the quantum computing opens all kind of interesting questions that are not yet fully understood and investigated. And so the limits to quantum computation. Okay, well, then let me just maybe conclude this first lecture with this. Of course, you know, we would like to build those devices. For two reasons. Either to see the more powerful quantum computation, which is today the primary reason. So we go to the lab, we build quantum logic gates, we try to set up and scale up quantum computation systems. Another reason, which I think is maybe not so often advocated as much as I would like, is that building a quantum computer is probably the most difficult experiment that mankind even sort of decided to set up. I can hardly think about anything else that is so complicated. You have to control so many components with such and such precision, and we are still, walking in the direction where we are talking about one protected qubit if everything goes well in the surface code. So there is a long way to go, but it may well be that if quantum theory is not the end of the story, and almost certainly, or probably we are all confident it's not the ultimate, we haven't reached the border of knowledge. There must be a better theory. There must be something that eventually will supersede quantum theory, right? So if that is the case, then we would like to see things to go wrong, right? We would like to see quantum physics failing at some point, somewhere in the experimental setup. And in my view, if the chances are that this may happen in this most sophisticated experiment that we are trying to set up. So my kind of, take on this is that I would love to see the whole program fail, but fail for good reason, fail in such a way that we can learn something new. That doesn't mean, of course, that we will not actually be able to build powerful computing devices, because if it fails, there will be a new post-quantum theory explaining things, and these post-quantum computers will be probably even more powerful. But when judging, trying again, sort of quite often to explain this to public at large, when you talk to journalists, they want to know exactly, where are we and what is actually stopping us from having a quantum computer. So then I like giving some kind of analogy to architecture in this case. I say, look, there was a significant progress in civil engineering that happened somewhere between the Greeks and the Romans. If you go and look at the ancient temples in ancient Greece, they're beautiful, right? So if you look at the Pantheon in Athens, it's truly beautiful. But from the engineering point of view, they are lousy, really. Because, look how many pillars and columns they have to support the structure there. Many of them, right? Because then you put those flat slabs of stones, and it's kind of heavy, and to keep it there, you need to support it everywhere. And that's not very impressive. And something really interesting happened between the Greek and the Roman architecture. Etruscans, many others also credited, came up with the concept of an arch, right? And having abilities to make arches and domes change the architecture completely. So if you compare buildings in Rome, for example, they already had this concept of a dome, and they didn't have to use so many pillars to cover a huge space. But building an arch is not easy, because you have those piles of stones and you have to bend them at some point, and then they usually collapse, right? But then you just bend them again. And then there's this key stone that you have to put, and the physics starts working for you eventually. But to reach this threshold is very difficult. And so the similar in quantum computation, if you think about quantum logic gates as your bricks, as your individual stones, and you want to build a beautiful fault-tolerant quantum computing device, so you start building an arch, and first you build a wall, and then just bending those things, curving them, putting them in a way that is just a whole stable construction, fault-tolerant, reaching this threshold where we know we can scale things up is not there yet. So we are still at the level of building walls with quantum logic gates, but hopefully we will just overcome those things soon and we'll progress. So I'm not going to practicalities. So I'll just maybe finish this lecture with maybe 2 puzzles for you. Easy, but well, way too easy in a way, because I didn't know that you know about completely positive trace preserving maps when I started this thing. So the first puzzle for you to wonder is, there's a simple proof that +1 equals -1. If you just look at this expression here, you can. So this was actually for you to practice complex numbers. So sorry, I just simply underestimated your thing. But anyways, it's a nice puzzle you can give to your students or to your friends. That if 1 is equal to square root of 1, and which you can write it as square root of -1 times -1, which then you can write it as I squared is equal to -1, right? So think about it. Another more interesting puzzle that is actually very good to practice, and if you're familiar with those are good. If you ever run classes for quantum physics or give lectures and you want to entertain your students, so this is actually one of the best puzzles that I like to understand the notion of quantum interference and a few other things. And this is related to the bomb testing problem. So I got it many years ago. Lev Weidman, a friend and a colleague, came up with this idea that imagine that you have a box full of bombs that have triggers, and those are super sensitive triggers. So the bomb has a trigger, you can think about it as a metallic plate, and even if a single photon goes into this trigger, the bomb will explode. But in this box, there are also some bombs where the trigger is broken, so there's no metallic plate and the photon just goes through and nothing happens. So those bombs are not good because they will never explode. And the idea is, given a box, some bombs are good, some bombs are not so good, can you select some bombs? I mean, if you are pacifist, you can turn bombs into something else. But originally the problem was formulated as a bomb testing problem. So I'll stick to this. So now, can you select a number of good bombs in such a way that it's not like trying post factum to figure out which bomb was good, which one was not. If it exploded, it was a good one. It's useless, right? We want to select some bombs that we know for sure they are good. And can you do this? And so this is actually a bomb testing problem. And there was interesting sort of like a story around it. So if you know this problem, fine. If you don't know this problem, think about it. It's a school, so in your spare time, you're supposed to wander around, look at the beautiful sea and think about mathematical and physical problems. So this is one of them. So it was interesting sort of a story around it. It was Lev Weidman and his colleague Elitzer who came up with this problem. And I learned from Lev and also from Roger Penrose, who came up with another version of this problem. And then when we discuss it later, I said kind of jokingly referring to Lev, who is a little bit on the religious side. We came up with something called Shabbos switch. So people of Jewish faith are not supposed to work on Shabbos. They're not even supposed to start any physical process. So we thought that instead of a bomb, instead of a trigger, we just have a finger, and then you just raise a finger, and then we design a Shabbos switch, which means that you can start the process without being really responsible for this process. So it's like a bit testing the bomb. And so it's equivalent, and we thought, it's a cool thing. We are not going to patent this, but for people of Jewish faith, if they still want to bypass all the restrictions on Shabbos, they can use the quantum Shabbos switch and start the process. And that's, I thought that this would stay as a kind of a funny discussion. But Roger was then writing one of his books, The Emperor's New Mind, the second version. And he wrote about this discussion in this book. And then, you know, I got a letter from a rabbi from New York saying, you know, just like, how come, you know, can you just, you know, explain this? You know, it's an old-fashioned handwritten letter, very nice one. And it sort of started almost, you know, a Talmudic discussion among this community, whether this is kosher or not kosher, whether you can really just bypass the things or not. And so, so it was actually fun to, finally, I think, they were happy to resolve that you are still responsible in some way for the process if you do this with your knowledge and so on and so forth. So you cannot just escape on technicalities. Anyways, I think that with those two problems, I'll stop maybe the first part. Tomorrow, I will talk about Bell inequalities. So, you know, to summarize, today I wanted just to give you the fun lecture. You came to beautiful Okinawa. It's the first lecture. Many of you are jet lagged. I'm also jet lagged. So, so this was about a little bit of history, a little bit of context, a little bit of fun stuff for you to enjoy. I think things will become much more serious. And tomorrow I'm going to use slides as well and talk about Bell inequalities with maybe a little bit, in a little bit more advanced way, but still it's going to be pretty much fun lecture. On Thursday, the last two lectures, well, we'll see how it goes. Maybe I go on the whiteboard and we'll talk about, maybe not about completely positive trace preserving map, but about, the idea was to talk about things like device independent quantum crypto and how we understand it and how it works. Unless you have any wishes, I'm also happy to adjust those lectures and cover. So you can just drop me a line. This is like artur.ekert@gmail.com. And if I get any sort of wish list by Thursday, I'll be more than happy to accommodate it. Okay, so any questions about whatever I said? Yes, please.
So I guess kind of intuitive reason that we don't have any algorithms is that when we think algorithm, we're kind of thinking that classical logic, step by step. Then to come up to the quantum algorithms, we need to think of step is you create a position in some way that gets you an advantage.
Well, you know, again, it's very difficult to say. So let me give you one example. People ask questions like, what kind of mathematical problems are good for quantum computers, in a sense that we can expect some sort of advantage when we design quantum algorithms. So one way is one intuition, if you have this picture of quantum interference, many computational paths, one way to think about this is, okay, most likely problems where we want to see sort of like contribution not from one computational path, but many of them, because then we can probably see the difference in the interference. So probably we are looking at some global properties, like global properties of functions, right? So we evaluating function in one point is, you know, as good for quantum as for classical, but we can ask questions like, what's the period of the function? Periodicity estimation is good for quantum computers because it requires, classically, we have to compute all of them. In quantum, you can, and you know, in classical computation, in order to estimate the period, you have to know the values of the function. In quantum, you can measure the period without knowing the value of the function, which is interesting, right? But this insight, this intuition is correct. But sometimes, you know, it just, there was an interesting example in the history of quantum computation. Shortly before Shor's algorithm, there was Umesh Vazirani and Bernstein came up with another algorithm about looking at whether a function is constant or balanced. Never mind this. Charlie Bennett, who has a really good intuition about quantum computing, wrote a piece for Nature, News and Views, where he was describing this Vazirani contribution, and he said, look, This is perfect for quantum computation because it refers to global property of a function, whether it's balanced or constant. In contrast, we'll never probably come up with factoring algorithm on a quantum computer, because if I divide a number by another number and check the remainder, whether it's 0 or not, like, because one way of thinking about how to design quantum algorithm for factoring was like this. Give me a number, I start dividing this number by 1, 2, 3, 4, 5, 6, 7 in superposition and check whether the remainder is 0. If there's 0, bingo, I have the factor. But this comes only from one computational path, and you will not see the answer to this. So you see, Charlie thought that this was the only way to approach factoring, and therefore he went public and said, quantum factoring is not good for quantum computation, and he discouraged a generation of people working on this problem, and therefore, but a year later, Peter Shaw comes and say, look, here's quantum factoring or discrete log. And the reason for that was, so Charlie's intuition was correct. What Peter did, he just took this problem and showed it can be turned into a global problem, like periodicity estimation. So what exactly makes designing quantum algorithm difficult, I think, is a combination of two things. You have to understand and have a pretty good intuition of how quantum computation works, so the quantum part, but also be able to see equivalences between different mathematical problems in mathematical terms. And combining those two is not common, because somehow people are educated either in quantum or mathematical. Is I think only your generation now is kind of exposed to both fields at the same time. So you are much better positioned to make a real progress in quantum algorithms than the pioneers of this field. Any other question you may have? Well, if not, then I just let you relax. Oh, yes, please.
I have a really easy one. Your title slide with that beautiful picture.
Which one?
Oh, your very first title slide with that beautiful picture.
Oh, the, okay, this, yeah, I can just.
I'm just curious where you got that.
How I got it?
Yeah, where'd you get that picture?
Oh, from the internet.
Well, I figured that much.
It's one of those, it's actually a 19th century, I think, quite a lithograph or whatever, this one, right? Yeah. Which I like it because it sort of like shows a traveler, medieval traveler, so poking the head through the celestial sphere, looking outside and trying to see the unknown world. So that's what we are trying to do, trying to poke our head into the quantum world. This is the classical, this is quantum to me, right? That's my free interpretation of this picture, not intended by the author. But David Deutsch and I wrote a piece for Scientific American where we use this picture. So I can send you a link to that, where you get the picture and you get the article. 2 in 1. I'm glad you like it, by the way. I think that people from, I don't know whether our colleagues from industrial side have any questions or comments to all those geeks working on something that looks pretty abstract at the first glance and can eventually be practical. But if you don't, I'm around most of the time, so most welcome. Drop me a line and come and ask. If you... Oh, yes.
Square dot gates. So was it more like a story like challenge to go to and then you went to the lab and the meeting with the lab, or did you have the experimental results and then try to?
Well, no, we didn't have any experimental, so we knew that it was our way trying to provoke people on the logic side. We knew that we have this kind of gate. It's rather trivial to implement it in the lab. And then you go to logicians and you have to tease them because, they are so full of themselves. They think they understand it all. I mean, they're nice people. But it was just, of course, it was just a way to attract the interest. I think we need people. This field is a very Catholic field, Catholic with small c, like all-embracing field. which needs contributions from computer science, from logic, from mathematics, and from everywhere else. So it's truly interdisciplinary. And I think for us at some point, it was when it was important to have mathematicians on board. So you talk to them, and how do you encourage someone? You have to provoke them something, show them something that they deeply disagree with, at least at first, and then they start thinking about it. So that's how it happened. And of course, it was, I don't think I ever had to go to the lab with a logician to show the person a device that would do this, but of course, it's relatively easy, even a beam splitter or whatever, that there are simple devices that will do the job, but they had to be explained in a quantum way. Okay, well, thanks, and yeah, please.
I have quite a few questions to Artur, but with regards to the computation about trust process, the process that a computation logical, it's quite interesting because in QPD that's very important. When you trust what is going on in each step, using the criteria of security reasons for those doing what they said it to do. But I wonder whether, from maybe from a logical perspective, physically it seems quite trivial to test those small problems or use benchmarking.
Yeah.
What's your actual opinion? The answer to that?
Well, it's just, there's slightly different ways of trusting what's going in the device independent scenario, and somewhat, but you're touching up on a much bigger problem, in fact, in quantum computation. It's just a question of verifying your computation, whether this really does the job, whether this, if something is not NP, right? So you work hard to solve the problem, but it's equally hard to verify that whatever you have is correct. And so how would you verify that your quantum algorithm is doing what it's supposed to be doing? And then there are a few tricks. Interestingly enough, some of them are taken from the crypto community, namely to embed randomly, to embed some subset of data to which you know the answer. And as progress the computation, if it just goes off the rail, then this will be messed up. Most likely, with a high probability, this will be messed up. So there are ways of doing this. But of course, device independent in some sense is it's kind of easier. Well, at least up to local isometry. So it's easier because, going into technical way. So that if you measure certain properties, usually you can think about a set of linear functions that attain maximal value, right? And you know that, like on a convex set, the maximum can only be reached at one point. So you know that we can talk about it in details, but in using sort of hand-waving arguments, there's a solid mathematical stuff and underlying physics, which kind of shows you that the system must have been doing something that you expect, because it's reaching a certain maximal value up to the error rate or whatever. So that is, I think, much more easy. I think I can see that this can be easier explained, and my confidence in that would be much higher than a confidence that the quantum algorithm is doing what it should be doing. Because those tricks, I also don't fully understand all the techniques that computer scientists came up with, so it's very difficult for me to explain them in a clear way. But one or two that I know, I'm not so convinced that it just works this way. I think you probably base the whole thing on the trust that the whole thing does what it does on the basic, that you construct it from the first principles, and therefore you understand the underlying physics and should be doing what it should be doing. That's what. Okay, I just let you go and have some coffee now.